In this video, we'll be looking at more applications of the exponential function, specifically compound interest. Compound interest is a very specific economical mathematical concept that we utilize. It happens in a very specific way most of the time, and in other cases we might use specific functions. So there are two specific functions that we can use for compound interest. The first one you might recognize as a equals pe to the power of rt. So it's very important that you understand that this is a base, this is a multiplication on the base, and these are the exponents in that base. This is what we would call continuous continuous compound interest, whereas we might have something that is not necessarily linear compound interest, but it's compounded based on a certain number of times. So we have a n equals number of times compounded. And that's going to be a equals, and this one's a little bit more trickier to follow. We have p, again, the same p as we have over here. That's what we call the principal, the amount that we invest. 1 plus r over n to the power of nt. Okay, so now all of the variables that are in common between these two are exactly the same. So the values that are the same are a is equal to the amount we end up with. Okay, amount at end of a certain amount of time. End of time. We have p is equal to the principal, principal being the principal amount that we invest. Okay, how much money we're putting into that account. Your r is going to be the interest rate. Be very careful with the interest rate. A number of students can make mistakes in terms of how we write that. If I tell you that the interest rate, the rate is equal to 8%, that's a phenomenally large interest rate. Something you might see on a credit card, maybe not on a savings account. But the interest rate of 8% will convert to an R value of 0.08. Again, you have to convert this appropriately to what it really is. 8% is really 8 out of every 100. 8 out of every 100 converted to the appropriate decimal would be 0.08. So that's your interest rate concepts. And then you're going to have t is equal to the amount of time. So the time in years, it's compounded. And then lastly, n. n doesn't exist, you'll notice, in the continuous function, because n in the continuous function is, for lack of a better phrase, infinity. It is the value that just continues on forever. You've compounded it continuously for every second of every minute of every hour of every day of every year, and so on and so forth, getting as small as you possibly can, going even smaller than seconds, but milliseconds, and so on and so forth. But n is the number of times you're compounding this in a single year, in 1 year. Okay, it's very important that you identify that, because this right here, these two things together in this formula are going to change things. So that's your setup for these problems in terms of knowing the formulas. Now, you're going to pick between one of these two formulas based on the way that the question is worded. So if we take a look at an example, for instance, let's say you decide to invest, let's say $10,000. So you're going to invest $10,000 into an account. You're going to invest it over, let's just say, let's say 4 years. You know, the time that you might be in college. Let's say that you've taken the $10,000 in terms of a student loan, and then you're going to put the excess from your student loans into an account. So the $10,000 is what you're putting into your account. So you're putting it in there for 4 years. Now you have a chance to pick from multiple different accounts. The first account is going to tell you that you can compound it continuously, and I always abbreviate continuously using Conti. Okay, it's compounded continuously, but the interest rate on that one is going to be, say, 5%. On the other one, the other account that you have to choose from, it's going to compound. We're going to go with compound biannually. And the reason why I'm going to choose biannually is because it's important for us to designate how these things generally refer. It could, when said biannually, could also mean semi-annually. Those are generally intertwined and used together. So you have one account that's continuously compounded 5%. You have a compounded biannually, but we're going to go ahead and say that that's at, let's just go 6%. Let's do something smooth. Okay, so with all that being said, you know how much you're investing, you know how many years you're going to put it in the account for, and you know your interest rate. The biannually also is important. The biannually simply tells you your n value is going to be 2. Biannually and semiannually, again, are interchangeably used, even though they might not appropriately be interchangeably. But you'll notice that depending on the number of times it's compounded in a single year will change the way that this is. So if I say that it's compounded daily, you're going to say that n is 365. If you say that it's weekly, you're going to say that n is 52, because there's 52 weeks in a year. You will never take the assumption that there is a leap year of any sort. You could say daily, weekly, yearly, monthly, and again, there's all different sorts of ways you could set this up. But these are the two accounts that you're going to be given. So in other words, we have to go ahead and set up these accounts. The first account is how much money. That's the real question, is how much money are we going to have after we've invested this $10,000 into these two accounts. So the amount A is going to be how much we're going to get back. The P value for this is obviously the $10,000. The time, the T, is the 4 years. Continuous, again, tells us that we're going to specifically be using this formula over here, A equals P e to the RT. Compounded any other way, again, compounded any other way forces us to use this formula. So part B is going to use this one, part A is going to use this formula. And then my rate is, again, 5%, but I have to make sure that I convert that appropriately. So if I'm going to use this formula here, E to the RT, my P is going to be the $10,000. E is always E, it never changes, it's always going to be that 2.7 whatever, blah, 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 blah. My R is 0.05, because again, I have to remember that my rate is not the interest, it's the interest converted to the decimal equivalent. And then I have to plug in T, and T is 4. So in this particular case, I'm going to go ahead and type this into a calculator and get myself an answer back. For part B, I'm going to do the exact same thing, but this time I'm using this formula. Be very careful, that's R over N and N to the power of T. And when I plug everything in here, the only change is that I have an N value that doesn't exist in the, again, continuous compounded function, and I'm going to go N is 2. So my A is going to be, I'm going to go ahead and do A equals the amount that I'm going to end with. My P principal is 10,000 still. I have 1 plus my rate is going to be 0.06, not 0.05, over N. N is going to be 2. Up here I'm going to have 2 times, and my T is 4. Now you'll notice up here in this exponent should end up being the number of times you in total compound this interest. So in this case, if I'm compounding it twice a year for over 4 years, I'm going to compound it a total of 8 times, which should make logical sense. So again, the question generally revolves around which of these two accounts are better for me to use. And all we're going to do is turn to my calculator and type these in very carefully. So I'm going to have $10,000 plugged in. I'm going to go ahead and use my exponential function right here, e to the power of my r. So I'm going to be very careful about this. I'm going to make sure that I type an extra set of parentheses, 0.05 times, and then 4, and then end the first original set of parentheses. When I hit enter on this one, I'm going to have to approximate it, otherwise it's not going to give me the right value. And this looks like it's automatically rounding. Let me check to see if I have a way to fix that. Let's try that one more time. There we go. So that number there is $12,214 and 3 cents if I round it to the nearest decimal. Now again, depending on how it asks, it's generally going to ask you round to the nearest dollar. Again, sometimes it might not ask you to round to the nearest dollar, but if it doesn't tell me to round, I'm going to round to the nearest cent, simply because that's how much money and that's how small we're allowed to calculate data. On the second one, again, we're doing the same thing, but we're going to be really careful about how we plug this in, making sure that we use parentheses very accurately and very carefully. So I'm going to have the $10,000 again. I'm going to go ahead and multiply that by this is the part where you got to be careful. 1 plus, I'm going to use some extra parentheses here. Now, it might be better if we take these numbers here and simplify them down first. For instance, 0.06 divided by 2 is really just 0.03. So I might just go ahead and do that 0.03 instead, and then take it to the power of, and rather than doing 2 times 4 in the exponent, why don't I just go ahead and use 8 there. There's nothing wrong with that. It's all the same stuff. Making sure that, again, the parentheses are encompassing the 1 plus the 0.03, and that parentheses that are encompassing that are all to the power of 8. When I hit enter, I'm going to get the amount of approximately 12,667.70 when's all said and done. Looking at these two, you'll notice here that the interest rate of 6% is a better account over an account compounded continuously. So continuously does make a difference in how we compound, but it doesn't compound nearly as much. So for instance, if I were to change this ever so slightly in the problem, rather than using a 0.06, but I used a 0.05 here, again, let's take a look at how changed these actually become. If I change this 0.03 to a 0.025, because that's really all it changes by, and I hit enter, 12,184. So this one ends up becoming, so continuously is generally a more compounded and better for our account investments when we're trying to obtain money. However, you'll notice by maybe $30 is all it changes over the course of those 4 years. Now, over the course of a longer period of time, sure, it'll change more. But for this particular case, again, the 6% interest will have a stronger effect on an account than the way that we compound it. Again, by $30 difference here versus the almost $400 difference, or more than $400 difference here. So that's how we deal with compound interest. That's how you would use both formulas. Again, the most important piece is to identify which formula you're using and how you're using it. Again, don't forget for this one right here, there's an end value that you have to account for, basically how you're compounding it: daily, weekly, monthly. Monthly would be 12, and so on and so forth. And then we have compounding continuously, which are just plugging values into and evaluating quite efficiently.